Okay, gang, good morning and welcome to another AP Stats short video. Today we are going to come up with our very first regression equation, kind of by hand, just kind of walk through the process and learn how it works. So I'm going to bring up a screen to share with you. We're going to talk about the heights and weights. I'm going to move my picture around. The heights and weights that we had talked about the other day, they were on my calculator as of yesterday. We found the means, we found the deviations, we found R. I'm going to trust that you remember those numbers. I'm going to trust that you remember the average height, I believe was 70.96 inches. I believe the average weight was 153.6. The deviations were 2.17 for height and 21 pounds, give or take, for weight. And I believe our correlation coefficient was 0.75. So you have all that information written down in your notes. So when I refer to it, you'll know what the heck I'm talking about. So that's what this says. Refer to your saved height and weight information. We'll use it to find a linear regression by hand. Look at this. Look at this right here. This is y equals mx plus b, right? Mx plus b. I wrote it in a slightly different order, but basically this is your slope-intercept equation that we're going to work with today. So here's where we got to start. This is the moment. This is it. We said yesterday that if we had a new student coming into our class and all we knew was that student was one standard deviation taller than average, we would naturally predict that that student is also heavier than average, but we wouldn't predict that he or she was a full deviation heavier than average. We would back that off. We'd regress that. We'd head back toward the mean a little bit. And how far we would head back was based on R, the correlation coefficient. So we found R to be 0.75. So if we have a dude coming into class that's one deviation taller than average, we're going to predict that that person is 0.75 of a deviation heavier than average. Rth of a deviation heavier than average, you might say. So that's what I'm showing down here. I'm showing the slope calculation, and take a good look at it. If there were no R right here, this would just say rise over run, right, in terms of deviations. If I went up one deviation in the x direction, I would expect to go up one deviation in the y direction. That's if we had a perfect correlation. But we do not have a perfect correlation. We have a 0.75 correlation. So we are modifying the y deviation by r. So it's a really simple calculation. The weight deviation is 21. I'm pointing at it. The height deviation is 2.17. And so if somebody's 2.17 inches taller than average, we don't think they're 21 pounds heavier than average. We think they're 0.75 of that heavier than average. That's our prediction anyway. And so when you work this out, you get I'm going to call this 7.3. And so the interpretation is going to be very easy for this slope. We're going to say something like this. You might want to write this down. Based on our model, good way to start, put a comma there. Based on our model, for every inch a person is taller, that person tends to weigh about 7.3 more pounds, give or take, approximately, but I'm not really sure. So we got to put in some fluff words because we're definitely not saying this. If a person is 1 inch taller than somebody else, he or she weighs 7.3 pounds more than that person. That's just not a true statement. That's our best fit line slope based on our model, but we got to put some fluff words in that. So I'm going to say it again. I might say it slightly differently. Based on our model, for every inch a person is taller than somebody else, that person tends to weigh approximately 7.3 pounds more, give or take, about. All right, so that's our interpretation of the slope. You will remember that when we had z-scores last time, the slope was just R. Well, why was that? It was just R because when you have z-scores, your standard deviation of y is 1. All standard deviations for z-scores are 1. And your standard deviation for x was also 1. So we had R times 1 divided by 1. Well, hello, that's R. So if we had z-scores, the slope was just R, but now we don't have z-scores. We have real things. We have pounds and we have inches. So this slope is going to have a label, 7.3 pounds per inch. Okay, go back to algebra 1. Think about once you had the slope of a line, how'd you find the y-intercept? Well, hopefully you also have a point. That's an easy way to do it. If you have a point, then life gets really good. And so we said last time, there's one point that is always on a best fit line. Always, 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 every time, never fails, always on a best fit line. And that is the mean point, the average point. So somebody that's average weight and average height, that person, that thing, that spot is always on the best fit line. Well, we have that. The average height was 70.96. The average weight was 153.6. We can use that. So if you slide down a little bit on your notes, I know you're looking at it already. Where is it? Ah, that showed up. So here's what this says. We can use Y bar, remember what that means? Average weight, and X bar, which means average height, to, of course, write this. We're going to fill in the average weight. Whoopsie. We're going to fill in the average height. We just found the slope. Look at me using all these labels. Isn't that delightful? The only thing we don't have is right here, the y-intercept. I'm not going to do this arithmetic for you. That's pretty basic arithmetic. But if you do, you get negative 364.4 pounds. And you might say, well, that's a weird number. I don't know anybody that weighs negative 364 pounds. You also don't know anybody that's 0 inches tall. And so think about the interpretation of the y-intercept in this particular case. Usually a y-intercept, always a y-intercept, is where x equals 0. Well, x is the height. So the y-intercept is meaningless in this point. It's just a starting point. It's part of our equation that helps us make predictions for the heights that actually do make sense. And so please do not tell me, the y-intercept means that if you're 0 inches tall, you probably weigh about negative 364 pounds. Don't tell me that. It's just a starting point. Now, there's one thing missing from this final regression equation. Look what I have. I have used a label on the y. I've used a label for the x. I got my slope. I got my y-intercept. I'm missing one thing, and it's because in Microsoft Word, I guess I couldn't find this symbol. I hope you recognize that I'm missing something over here. I should have a hat above the word weight because it's a prediction, right? So how I would read this final regression equation is this. It's kind of fun. You would say weight hat equals negative 364.39 plus 7.3 height. That's my final regression equation. Okay, so that is one from start to finish, how to make a regression equation. We're going to stop this video right here. There's more to come for sure, but that's an intro. So, ta-ta.